the 1-2, that's what I think that's the part we're on right now. That's our PowerPoint slides. Like if I go up to here.
Yeah, it says.
Yeah, 1-2A. I know it's confusing.
So are those due on Friday then, or
This assignment 1-2A will probably be due Friday.
Okay.
It's always due when we get through it in lecture the next time. Good question.
I'm just making sure.
So what I've been doing also, I think I might have shown you guys this. Like if we go to our Canvas page now, and actually that if I know I asked you if there was homework due and you guys told me yes, but if I forget, this is where I look. So right off the bat now, look for the stars. Go here. Yay. Okay, so right here, it says section 1-1_1B will be due today.
You tweet about when assignments are due?
Yeah, because she's like, you tweet about that? I'm like, yeah, because
I'm gonna follow you.
it's just for this class. Yeah, if you want to follow me, then you'll get these pushed out there on Twitter. Do you know what I'm saying?
I bet you got hella followers.
I
All
have,
these kids that come to this
I have
class
like
are
4
like, oh,
followers, right? Yeah.
yeah.
I don't have very many.
Rip.
Yeah,
I have 4.
Yeah.
Rip.
Yeah, I know.
Wait. Okay. Do you have?
So it's
One on one
EA
account?
Snipes under. I do.
Okay.
So one for each class.
Because I found your _psi one.
Yeah, my _psi one. Yeah, it's all captures all. Otherwise, it's underscore whatever class you're in.
Okay.
Okay. All right. Yeah. So sometimes students I say, "Well, how far did you get?" And I always go to my Twitter feed because it's a blur sometimes.
I'm gonna turn off push notifications.
Oh, I feel so important,
I just need to know when these things are due.
right? So here and there, I kind of talk about what's going to be on the test. And let's see, did I already told you one term? I think I might have said the ecliptic was going to be on the test, maybe, of some sorts. And another question that's going to be on the test, either, did I tell you the format of your tests? Your tests are going to be multiple choice, short answer, and then the last one is like, wait, not that, multiple choice, fill in the blank, short answer.
So no essay?
No essay. The short answers are kind of essay in like 2-3 sentences. Yeah. So, yay, I see somebody's happy. So the term parallax is kind of important to astronomy. So it's remember parallax, what you guys did on Monday where you kind of did this, you close one eye, close the other eye, and then when you hold out farther, you guys told me it doesn't move as much, okay? So the point is, as the object of interest becomes closer to the background and farther from the observer, you don't see it move much when you move side to side as the observer. How does it make a difference in astronomy? Well, here's how it makes a difference in astronomy. So here we have what we've been talking about. We have the Earth orbiting the sun, excuse me. We have the Earth orbiting the sun. Now, usually stars from Earth's perspective make those cool shapes like the constellation Orion, or they make cool shapes like the Big Dipper. Okay, they're just a set of stars. But if one of those stars is kind of close to us, guess what? As we relocate 6 months apart, so here we're in July and here we're in January, as we relocate, if the star is relatively close, like shown here, you're going to see it move against the background stars. Okay, that's called the effect of parallax because it's relatively close to you. As this star comes farther and farther away, becomes part of the background stars, as we relocate 6 months apart, it's not going to wiggle. One of the things about stars that we like to note to characterize a star is how far from us is it? And this is one way to see how far it is from us. The amount that it wiggles, actually it's an angle, is an indication of how close or how far it is. The bigger the angle, just kind of like if you hold your finger here, the bigger the angle, that means it's relatively close. The smaller the angle, that means it's relatively far away. So it's a math thing. Again, I don't do math in here, but it's not a hard math problem. Okay, so that's kind of good. Most stars don't move against the background stars, but if you do. And so I think this is quite clever. You see these two little boxes up here on this figure. They're showing you a box on the right as we would see it in July, I believe. So here we are in July. This is how we see that star of interest. Here we are 6 months later, and here's where we see that same star of interest. So it's shifted. Thank goodness we don't see a lot of shifting. Otherwise, we couldn't have those awesome sets of stars that we so enjoy. There's just something about looking up at a set of stars when you're like out of town. You're like, oh, it's just reassuring. You're like, everything's fine. Yeah. So anything on my slides is fair game. So I'm going to emphasize a few constellations. I think I've already talked a little bit about constellations. When I get the test made up, I'll kind of narrow it down. But anybody in here a Leo? I'm a Leo. So let's just go around. Virgo, Libra, Leo the Lion, Cancer, Aries.
I don't know how to say it. It's like
Sagittarius.
Scorpion.
no,
Sagittarius.
yeah,
Oh, I'm a Sagittarius. Is it December-ish?
like November.
November. Okay. Sagittarius. So what are you? Do you know? What month were you
What's your
born?
birthday?
Oh, June.
So you're probably
You have to look it up.
probably Leo.
I'm June.
What is your birthday, June too? July. You might be a Leo. We'll have to look it up. Capricorn. Okay. So Leo is an awesome constellation. Leo has two parts to it, and I'm trying to think this time of year.
What do you think the baby at Gemini?
I don't think we might see Leo. Leo has two parts. It has the butt part, which is like a triangle, and it has the sickle part, okay, which is like the head. Big Dipper, big deal, Big Dipper. No, it is a big deal. Now, the Big Dipper, actually, some of you guys know, is not a constellation. It is, and I'll write it up here, so it's fair game. The Big Dipper is an example of an asterism. Sounds even more important than a constellation. An asterism is a subset of a constellation. Okay, so it's subset of CONST stands for constellations. What else we got? These are up. So when we go to look at stars, what is the 11th? September, I think so. September 11th. We go look at stars. Hopefully now we're gonna look at the stars from this area, so it's not real dark skies, but hopefully we'll see kind of the Milky Way. We'll see. Here's the Milky Way. And this sky right here, sometimes called the Northern Cross, is also called the constellation Cygnus. That constellation has two names. Like we saw before, sometimes we actually name the stars. So at the top of the Northern Cross, or at the bottom of Cygnus, is the star Deneb. And we have constellation Lyra up here, meaning the lyre, cool bright star Vega. And then down here we have the eagle, Aquila, and a bright star Altair. Those three bright stars, remember the other day we had the winter triangle? Here's the summer triangle. So we have Deneb in Cygnus, we have Vega in Lyra, and we have Altair in Aquila. Delphinius is almost as cute as Telescopium. No, Delphinius is cooler, I think, because actually it looks like a little dolphin. It really does. It's adorable. It looks like a little dolphin. So I'm going to kind of darken the skies. This is from our old home. And one of the things you can do with a camera is if you open the shutter, you can get a sense for some of the stars. Let's see, we talked about Orion the other day. And I don't know if you can see, it's hard to see. What do we got here? Yep, this would be Betelgeuse. Here's the 4 stars of Orion. It makes kind of the body. Here's the belt stars, and here is the sword stars. Taurus, if you look for, I call it a flying V. I don't know if you can kind of see the V there. You're seeing Taurus. The 7 sisters I mentioned the other day. otherwise known as the Pleiades, Messier object number, I think 45. But sometimes people call this, mistakenly, they call it the Little Dipper. Can you almost see like a Little Dipper right there? Okay, this actually is taken a different location. You can see a little bit of the Milky Way. One of the things about the Milky Way, I said, is like lots of stars, right? If you have binoculars, look at the Milky Way. But you can kind of see some of these dark lanes through here. Okay, those dark lanes actually are like clouds in outer space. They're what we call dark nebula. This is the Summer Triangle. Star Deneb, Star Vega, Star Altair. It's kind of hard to make out the rest of the stuff, I think. All right. Speaking of stars, I'll pass this around, but that globe I brought in is what we call the celestial sphere. I should have warned you, but you knew I have to turn the light on. So this globe is what we call the celestial sphere. And it's a model. We use models in science. Now, what do you think is wrong with this? Why does this not make sense? What does it suggest about the distance of the stars from the Earth? They exist that they suggest that they're all that far away. They exist that they're all the same distance away. Are the stars all the same distance away? But it works pretty good. So I pass it around. Let's start here. What do you think? The bigger the dot, what's that mean about the brightness? It's brighter. Yep. The smaller the dot, the dimmer it is. You can kind of see that yellow. What do you think that yellow part is? The Milky Way. Yeah. Yep. So what the celestial sphere does is kind of say, well, if the Earth's here, we basically have these stars that we see throughout the night, these stars we see throughout the year, and quite honestly, I'm trying to convince you this, these stars that we see based upon what hemisphere you're in. If you're in the northern hemisphere and southern hemisphere, we call that latitude. You'll see different stars. So, but collectively, they make this thing we call the celestial sphere. So it is a model. Okay, so the visible stars are painted on kind of that shell, and the Earth is in the center. We've talked about the Earth's axis of rotation. Hopefully this will stay in here this semester. Sometimes it wanders, and it's my fault it wanders. So is this this axis of rotation, is it straight up and down? No. What is, and this will be on your test too, how many degrees is it tilted? 23 and a half. 23 and a half, yeah. And actually, as that celestial sphere comes around, you can see that within there, it's tilted 23 and a half degrees. That's kind of fun. Okay. So here's the deal. As that comes around, with the ball, okay, I have the Earth around here and have the celestial sphere around the Earth, okay? Where this touches the celestial sphere is called the North Celestial Pole. Now here's the deal. Here's what astronomers do, or whoever wants to kind of coordinate themselves with what's the nighttime sky. They basically, and I think you can see it on the celestial sphere maybe, they basically take the celestial sphere and give it coordinates. So this is the North Celestial Pole, this is the South Celestial Pole. Where's the equator on the Earth?
Right in the middle.
Right in the middle, yep. If we take the equator and extend it out to the celestial sphere, that gives our celestial equator. Okay, so that's kind of how that works. I have a picture coming up too. So as that model comes around, you figure you gotta think of, well, it's weird to look at that model. And I couldn't figure out how to do it, and this is the first time I've had this for students. You should be able to take that Earth and kind of do a little twisty. Because how long does it take the Earth to spin once on its axis of rotation? To spin on its axis. 24 hours, yep. I know, I couldn't get it to spin. But the Earth, yeah, oh, you did it. Well, you spin it a little bit. Okay, there you go. See how she's spinning it? Yay! But the Earth is spinning in that celestial sphere.
Wait, where's the Earth?
Oh, that is the Earth.
I found it.
Okay. All right, so this is the celestial sphere. Do you buy that? This is kind of what you're passing around. Yes, and everybody loves the celestial sphere. I got it off of Amazon, so good to meet you.
We're gonna see this. We're gonna see this right here.
Okay, so we talked about, here's the Earth. Now, what's different about this figure of the Earth? Why does it look different to you guys? It's look different to me. What's wrong with its axis of rotation? It's straight up and down. It's not tilted. It's wrong. Well, I don't know if that's wrong. We're just trying to kind of tell you a difference in spatial. Yes. So we see the North Celestial Pole, the South Celestial Pole, the Celestial Equator. What is the ecliptic? What did I tell you guys the ecliptic was? The ecliptic was...
It's the plane with all our planets.
Yeah, the plane with all of our planets, exactly. This is going to be my sun, okay? And kind of this flat thing that holds all the planets as they orbit the sun. That's called the ecliptic. Alright. Well, here's one for you. Why do we have, how can we make sense of what is that little yellow dot? What is it? It's an important star.
Oh.
I said
the equator.
It's not the equator. It's the sun. It's showing you actually where the sun is, how the sun appears to move against the background stars. Yeah. I have a slide coming up here in a minute. We're going to talk a little bit more about the signs of the zodiac. But the way this works is if I'm the Earth, of course we're going to make that the sun. How does this work? So if I look beyond the sun, which I can't see the stars beyond the sun, but if I look at the stars beyond the sun, that in the month that I'm born, that's what sign I'm in. If we make this, let's see, we're going to make this, I'm going to tilt this way. Make this June, okay? Over here, we're going to make this December, right? Tilted axis of rotation, all that. So now when I look at the sun, it's here. I look against the background stars, the sun. That's in December. That must be Sagittarius. For instance, December and November. Okay, so that's how that works. So the sun appears to move against the background stars. So what they did was just take the celestial sphere and put it on the celestial sphere, what it looks like. Again, celestial sphere. Can't have too much celestial spheres. So here we see the tilted axis of rotation. We're going to talk a little more about some of these terms. It's called your local sky. So you can see this cute little person. Right above that person's head is called the person's zenith. So right above that person's head is the zenith. Now, is it going to change throughout the course of the night? Yeah. In fact, that zenith, let's see, as the how do I say this? The celestial sphere appears to rotate clockwise, even though we're going counterclockwise. If we look from the inside out, actually, it looks counterclockwise. I'll try to kind of explain that. So that's our zenith. And see the horizon. Again with the Milky Way. Nice, distinct picture. And I think I've said before, why does it look like this? It's all sorts of little tiny little stars, dust and gases. The dark regions, like I said, doesn't mean that there's nothing there. Those kind of like little striations in the Milky Way are there because they're actually dark nebulae. So stepping out of our solar system into something a little larger, okay, this could represent our Milky Way galaxy now. And this little box here is the plane of our galaxy. So it's kind of flat too. So some more pictures. All right. Zenith. This is a term you saw a minute ago. Okay. Zenith is the top here. If we want to describe something in the sky, like here, I don't know if you guys can see that, but here's the sun right here. This person would describe what we call the altitude. They would put out their hand to the horizon, and then they would put their hand up to the sun, and they would say what that angle is right there. And they're saying it's 60 degrees. Then to kind of pinpoint where that sun is, they have to go ahead and say the direction somehow. This person says the direction is southeast. We can get more specific than that if we want or need to. Right above the viewer's head is the zenith, looking all directions, the horizon, and the meridian is actually what passes through the person's north and south and goes through the zenith. So that's the meridian. That's kind of your finding your way around your local sky. Now, I don't want to get you confused because there's your local sky and there's also the celestial sphere. As I pass this around, you can actually give coordinates to an object where it is on the celestial sphere, but that's different than your local sky.
So just to be clear, your local sky is basically what you see when you look up. The celestial sphere is everything.
Yes, the celestial sphere is everything, and it's standardized for regardless of where you're at.
So can they not see past this? Like, is that how far they?
Well, here's the deal. She asked if they cannot see past this. Let's see. We can't, it depends on where you are. So, if you're at the North Pole, you can't see back here. You can't see past that. If you're at the North Pole, this is the stars you're going to see.
Yeah.
If you're at the South Pole, this is the stars you're going to see. So, of course, we're in between. We're about 45 degrees north latitude. So, we see kind of a little bit of, we see, I think all of these and some of these throughout the year. But at 45 degrees latitude, we can't see some of these. Like, we'll never see, there is no, like there's a Polaris, you guys told me, is a pole star. So right here, Polaris. Okay? Because our axis of rotation is pointing to it. But there is no pole star for the Southern Hemisphere. I don't know if that answered your question. So yeah, there is definitely one on my bucket list is to go to the island of Australia if I can put up with the poisonous things, because I want to see those sun and stars.
Oh, crikey.
All right.
Is that an accurate way of saying that? The island of Australia?
That's an island.
I mean,
it's a continent, more continent.
Yes, it counts.
It's a big island. I don't know. I'm not.
Just don't get attacked by a koala.
Don't get attacked by a koala. Oh, they're so
They're
cute.
very aggressive.
I love koalas.
Note to self. So one of the things actually we do at the observatory on a given evening, we might say, well, where is Venus? And somebody might say, well, it's hold out your hand and it's 2 hands up. There's where Venus is. We do it all the time. Yeah. So actually what we're doing is kind of talking about kind of degrees of the degrees, but like angles of degrees. So for instance, for a typical person, if you take your hand, if you put it out, the word is subtends. Your index finger subtends 1 degree. Okay?
But how is that like a, what am I trying to say? How is that like a popular thing to do? Because can somebody like, is there like a specific stance? Like what if you put your head too far up and then you put your hand too far up? Like
well, you're supposed to, it's relative to the horizon. So when we do it, it's like, so put out your horizon and it's like, what 20 degrees? Because if your fist is 10 degrees, so 2 fists would be 20 degrees. So 20 degrees up from the horizon.
So just look at the horizon.
Look at the horizon, yeah. But the problem becomes we have different hand sizes and we have different arm lengths. So it's definitely not accurate, yeah. So here's the deal. If we were generally going to extend our fists and look at the Big Dipper, which hopefully we'll see when we're out and about in a few weeks, the Big Dipper would be half of a fist. The Southern Cross, which we can't see because it's down here, would subtend 6 degrees. Here's one. Does the moon sometimes look bigger to you than others? Yeah. That's actually, and we'll do a little bit of looking at the moon when we're in class, kind of sit out and look at the moon. That's actually myth. Okay. Next time the moon looks big to you, okay, go ahead and extend your hand and put your index finger out, and actually the moon should only take up about half of your index finger, because it's about a half a degree.
Did you see the moon on Monday?
No, I don't
It was
think we
orange.
did. Was it orange? Was it kind of low when you saw it?
What about the supermoon? Is that like a?
It was like bright.
Was it kind of high for a bright orange?
Because normally it does look like a little orange and slow, but it was like,
You know what I wonder, what you're describing is if we have particulates in our air, that actually can give that glow to it. So I wonder if we have like forest fires that kind of give us particulates in it.
What about when we have the supermoon? Is that like a myth or what?
No, the supermoon's real. What the supermoon is, if I make that the sun, if I make that the sun and I am the earth, a supermoon, I don't think it can happen at new moon, but it's usually full moon. So my fist now is going to be the moon. So we have sun, earth, moon. So I'm going to go ahead and I'm going to put, this is the moon over here. We'll talk about phases of the moon, but this makes it a full moon. Because it's, and I know it looks like the earth is in the way, but actually the light from the sun hits the half of the moon and we can see the whole half, so it makes it a full moon. So what a supermoon is, just has to do with the fact that the moon is at varying distances from the earth. So a supermoon means that it's close to the earth, so it's a little bit bigger from our side point of view. It makes tides a little bit stronger. Supermoon means it's closest to the earth at what we call perigee, and it's full. Because sometimes the close point is here, but it's not full, so that's not super. But if it's full, close, super.
what about a blue moon?
Blue moon has a couple of different definitions. The one I go by is if you have a full moon, 2 full moons in the same month. 2 full moons in the same month. That's a blue moon. The second one's blue. Okay, so yeah, check that out. Coincidentally, now never look at the sun, never like, oh, that's the sun, I think I'll stare at it, or something like that. But the disk of the sun is about 1/2 degree. And so when we talk about eclipses, that actually works well for eclipses. So the disk of the sun, from our perspective, of course the sun's a lot bigger than the moon, 1/2 degree, the disk of the moon, 1/2 degree. So check this out. Okay, we get a solar eclipse when the moon goes in front of the sun. So,
That's like once every.
what's that?
So that's like once every.
I know, it depends on if you're willing to travel. They happen, they're happening less frequently because the moon's getting farther from the earth, but I think 6 or 7 times a year. Yeah. Okay. Oh, I didn't. I'm gonna go grab my. I got time. I'm gonna grab my earth. Some of you guys already know this, but we're gonna look at the earth. We're gonna see how you slice up the earth and give it. Okay, so you guys told me the equator is in the middle of the earth. So here's my earth. Notice the tilted axis of rotation. And I broke it a while back, so the bait, so I know. So I tried super, did I try super cool? Maybe not yet. Okay. So the deal is we go, of course, this is the northern hemisphere, this is the southern hemisphere, and we have what we call lines of latitude that go up north and lines of latitude that go south. Now, what degree value is the equator? What line of latitude? It is 0. Perfect. That is 0. So from 0, we go.
It goes to 10, I'm pretty sure.
Yeah.
10 up north and then.
Well, my point was going to be, as we go, yeah, you're right. So we are, so here we are. We are around here-ish, Midwest. I think we're about 45 degrees north latitude. So what latitude is the top? this is 0, what is the pole? 90, yeah, very good, 90, exactly, you got it. So this would be, what about, what latitude would this guy be here down here? 90, yeah, negative 90, or 90 south. Yeah, you got it, perfect. So that's latitude. And here's the deal, and it kind of goes back to the celestial sphere, what we're talking about. Based upon your latitude, how far you are from the equator, that's going to govern what stars you see. Okay, that's going to govern what stars you see. I'm going to try to convince you that if you're on the same latitude but a different longitude, you're going to see the same stars. So just with that in mind, here we go. We could take us, go around. Oh, well, there it goes. I think I superglued that one. Go around here in China. Okay. Oh, thanks. Okay. Down here, same latitude. They see the same stars. Okay. Okay. So this is latitude. Well, longitude, as some of you guys know, and I think it's on here. What did we do this way? Okay. Poor thing. Okay. So longitude, like the slide says, goes long ways. Now, you need, like here we knew how to start, right? It goes 0, and then it goes 90, and then here. Longitude is different. So longitude starts at, yep, I see a 0 here. It's called the prime meridian, and it goes through
England.
Thank you, yes, Greenwich, England. So that's the prime meridian. It goes from pole to pole, okay? And then from there, we go, what direction is this? East, yep, and we go west. And then we go east, we go west, and we meet at, one of my favorite things, dun, dun, dun. Can you guys see those dots right there? That's the international date line. Okay. So that's where,
So where everyone's
Time doesn't exist.
that's where everybody gets confused.
So where everyone is.
But notice they meet, what's that number? 180. They meet at 180, exactly. So you figure you go east, you go west, and you meet at 180. Okay, at the, approximately the international date line. But you see how that jigs and jags? Yep. So that's just bizarre. So you step here, you one day, you step here. Confuses me. But I don't know. We deal with it. So that's kind of
What?
We don't.
what's the we don't. Okay. Ooh. All right. So the sun. My mom goes nuts with this. She's like, just teach science. You shouldn't tell them the sun rises in the east. Well, the sun appears to rise in the east and appears to set in the west. Of course, the reason the sun looks like it goes across the daytime sky like it does is because the Earth is spinning. You guys remember clockwise or counterclockwise? Which way does the Earth spin? Counterclockwise, yeah. The Earth spins counterclockwise, and it orbits, all the planets orbit the sun counterclockwise. In the source letter E, ecliptic, in the plane of the ecliptic, yes. All right, so honestly, we'll try to see this a little bit when we're out in a few weeks. Have you noticed this before, like the Big Dipper? Well, first off, so that's north, right? One of these days, I'm going to bring a sticker, and I haven't been done. I'll put a sticker up here, and it's going to be the North Star, Polaris. Okay. The reason Polaris is so important when we look out in the nighttime sky is all the stars seem to rotate around it. So now it's not fast, so you're not going to get dizzy or anything. But for instance, and it goes, yeah, let's go counterclockwise. So for instance, if that's Polaris, I can make this the Big Dipper, okay? If I come out 4 hours later, the Big Dipper is going to be here. 4 hours later, the Big Dipper is going to be here, okay? It's going to make a circle around Polaris. Now, as I get farther from Polaris, all the stars do that. They make a circle around Polaris through the course of one evening. If I go ahead and go counterclockwise, if I make my circle big enough, by golly, I'm gonna bump up against the horizon. At some point, I make my counterclockwise circle, if you can picture all this, and then I'm actually making a circle that rises in the east and sets in the west. And this is all because the Earth is spinning. One more cool thing about Polaris, and I don't know if it's on this slide or coming up, we kind of talked about the angle thing, like the horizon, you put out one arm here. If I would put the other arm up to Polaris, okay, that angle right there tells me what latitude I'm at. So for us, it's about 45, that angle right there. If I was at the North Pole, and I made out the horizon, what angle would Polaris be? No, the opposite of 0. So like if I'm here, I'm looking up, it'd actually be at my zenith. So what angle is that? 90 degrees, yeah. Like if I'm at the North Pole, Polaris makes an angle of 90 degrees. And what latitude did you guys tell me the North Pole is? No, that's the international daylight. Okay. It's not 90, yep, it's 90. So it goes from 0 to 90, 0 to 90. Yep. So that's kind of how that works.
You're saying that the equator would be right in front of you?
What's that?
So you were saying the equator would be right in front of you then?
Yes, perfect. If you're standing here at the equator, trying to find Polaris, you'd have to look out on your horizon. So Polaris is like right there on your horizon. So what angle is that? 0. And if you're at the equator, what latitude are you? 0. You got it. So what's kind of fun in imaging sometimes is to make these star trails, and you're going to see a few of these. But this is actually, you open up your shutter and you do a little bit with your, because you don't want extraneous light, but you can see the trail of the star. And right in the center of the star, actually this is in the southern hemisphere, what's the South Pole star? There isn't one. Trick question. Yep, no South Pole star. So actually, there is no South Pole star. So this is kind of showing you, again, the celestial sphere. It's showing you the Earth in the center, not a tilted axis of rotation, but I can live with that. The Earth is spinning, and because the Earth is spinning, that's why you see actually the stars going around. What's up here? Which star is up here at the North Celestial Pole? There's letter P.
Polaris.
Polaris, yep. That's why you see them from our perspective going counterclockwise around Polaris. So this is at the North Pole, this is at the equator. We were just talking about this. Okay, at the equator, it's kind of weird, they tilted the whole Earth. At the equator, we said Polaris is at your horizon. And we're kind of in between. So I already kind of told you we make about a 45-degree angle with the horizon, I should say Polaris does. So you're going to see different stars. So these are my stars. Actually, this one, I think I subscribed to Shutterfly. Boy, they got me. I tell my husband, I'm like, oh, but it's free on Shutterfly. He's not, is it really free? They call it shipping, but anyway. So yeah, I went ahead and made one of these. So these are just like little dashes representing how far that star moved for as long as I was taking pictures. Actually, if you're curious, I think you take individual pictures of stars, and then there's free programs that you can go ahead and it will stitch the photos together, and it will show you the movement of the stars. This one, I just love the colors here. Isn't that pretty? You know, stars are different colors, and these were taken with just a DSLR. Nikon has products too, but this is a Canon Rebel. I didn't take this one, obviously. Pose for me, polar bear. But this is kind of fun. So this shows you if you're at the equator, sorry, not the equator, whoops, sorry. If you're at the North Pole, or the South Pole, but if you're at the North Pole, where is Polaris? Straight up. Yep, it's straight up. So that means basically, I kind of think of it as a bullseye. I have bigger and bigger, what they call concentric circles of stars. If I would make a star trail. Once I get down to the horizon, basically, I have stars going like this. That's exactly what you see.
Is it a misconception that Polaris is the brightest star?
That is a misconception. Polaris, have you heard of it? Polaris is not the brightest star. No, it's a good one, an important one, but it's not the brightest.
So if you get lost, don't follow the brightest star thinking it's Polaris.
Right. Yeah, if you get lost, don't think that the brightest star is Polaris and follow it. This one is, you're at the equator, so if you're at the equator, where is Polaris?
Right in front of you.
Right in front of you. So actually, to me, this, you must be looking either east or west. Does that make sense? So Polaris is right in front of me, so that means I don't even have a full circle. I have a little, I have a half circle, a half circle, a half circle with my star trails, a half circle. Now when I get to east and west, guess what? I have a half circle. And so actually that's kind of what that's showing. And this is kind of what we see. We're like Goldilocks and the Three Bears. We're like the baby bear. This is kind of showing you that movement of, I better count lights. So it starts with letter A. What is the Big Dipper? It's not a constellation. It is a asterism. Yep. Asterism.
Yeah, me too.
The Big Dipper is an asterism. It's actually from the Big Dipper from the Big Bear, which actually is Ursa Major. So we see, and this is an important relationship that I'll kind of be pointing out in a given evening. If you can find the Big Dipper, you can find the Little Dipper. If you can find the Little Dipper, you have found Polaris. So here's how this works. Okay, so we have the Big Dipper. The Big Dipper has two parts. It has the handle. This is the handle. And it has the bowl. If you use these farthest bowl stars, it will point to the star Polaris. And the star Polaris is in the asterism, the Little Dipper. And so Polaris is in the handle of the Little Dipper. And of course, the bowl stars are really hard to see. So bottom line, if you can kind of see the little ghosty part, well, I guess it's not a really ghosty part, it's kind of showing you the Big Dipper starts here. This is the second position. You can see it. This is the third position. This is the fourth position. Each position is after 2 hours. Okay, so you can kind of see how it's going counterclockwise around Polaris, just like I showed you up there. This is a look at the southern hemisphere. There is no South Pole star. Seems like I should make it a question on your test. I don't know if I will or not. So we don't see a lot of the constellations in the southern hemisphere. We can't see this one because it's too close to the South Pole region. But they have a little cross too, and they can use it to point to their place of rotation. We're lucky. So I kind of finish up with this idea. So this is what I tried to explain a little bit ago. Of course, you see the sun, and you see the Earth orbiting the sun once a year, right? And you see it going counterclockwise. And this is what I tried to show you. In June, for instance, the sun passes through the constellation Taurus in June. In August, the sun appears to pass through the constellation Cancer. To me, it's a little confusing because you can't see Cancer in August, okay? But the sun's passing through. This is where I get people all riled up since I've kind of talked about zodiac signs and all that. So you probably see your zodiac sign, but it might be a little off.
Pop, I am.
I know.
Let's go.
The reason is because when years ago they picked out the 12 signs of the zodiac, there's really 13 constellations that the sun passes through.
Yeah.
Nobody's an Ophiuchus, okay? And by inserting that 13th constellation that the sun appears to pass through, it kind of threw everything off. So if you want to pretend this slide does not exist, I'm fine.
Yeah.
Okay?
So I'm not only
Wow. No, you still are.
I'm a Gemini. Let's go.
So, wow. I guess, is there just one question here? That's all I'm seeing. Well, yeah, look at that. So this will be due on Friday. Yep. Let me know if you have any questions. How about that early? Well,
Like
that
a
clock's
minute
wrong.
early?
I know, that clock.
You got a minute, you want to talk about the question? You just want to give us the answer for a minute?
No, you guys
No.
think about it. Kick it around. Look back at you're fine. You got this. You got this.